Thank you. This has been such an incredible conference, and we're going to present something completely different. We'll see how it goes here. But Ben and I teach a class together at the new school, and the reason we're presenting together is that Ben knows the psychology stuff, and I know the game design stuff. So we're going to trade off when it comes to our areas of expertise, I think. So the course that we teach is called Perception in Virtual Worlds, and it's at the new school at Parsons. So as mentioned, I teach game design. I also have a game design company called Local Number 12. You can play our game Dear Reader on Apple Arcade.
And I teach in the psychology department, where we have a new applied psychology and design concentration for our MA students, and this course is one of the electives that they can take to get a little bit of research experience in this area.
So here we are at opposite ends of the court. So one of the things that, obviously this is a great combination, design and psychology, is really where UX happens, right? Is somewhere in the middle of all of this. And interestingly enough, within both of our practices, we share some methodological similarities too. I write a lot about the iterative game design process, and that's what I teach, and Ben.
And science is inherently iterative too. I mean, I think even earlier today, Mike was talking about how designs are a kind of hypothesis, which then gets refined through feedback or data. So it really is a very similar project, testing a scientific hypothesis and building a design that you think is going to have some effect on people.
We're going to show you some examples of student work. I think these are all little videos. And these are experiments that students have done, oftentimes two conditions, which is why you see sort of pairings of these videos. As I mentioned, the class is called Perception in Virtual Worlds, but the experiments our students do aren't just in VR. We do have a sort of moment at the end where we talk about and do experiments in VR, but we're going to share with you the virtual worlds of video games, which in fact are the sort of first, virtual worlds in a way. But maybe not. Isn't perception a virtual world, Ben?
Yes, indeed. We don't see the world exactly as it is. In some ways, perception is a kind of useful fiction model of the world. And so we're already living in a virtual world of sorts, and game designers are designing in concert with the brain's kind of native physics engine for rendering the virtual world. Who goes here? Oh, yes. And that's a good segue into the general way in which we think about our players. We think of players as having cognitive models, a term that has already come up today. And we try and approach this in a nuanced way where we talk about specifics, models that they have of different components of a game as they're interacting with it.
Any game designer worth their weight in gold? I don't. That's sort of mixing metaphors. You have to start with the rules and goals of a game, and this is oftentimes what players are trying to apprehend and understand early on in the experience. This image, by the way, is from my book, Games Design and Play: An Iterative Approach to Game Design, which I'll show an image of later. So the first assignment we give our students is really, fairly simple. We don't ask them to make a game. We look at games that have been designed and that are short enough to be able and simple enough to be able to study. This game, Microforestry, is a game that Amber Chen and Lacey Shelby took a look at. These are pairings. So Amber is a design student and Lacey is a psychology student. This game was made for the Climate Jam, Indiecade's Climate Jam. I also volunteer at Indiecade, run their jury. So just briefly about the game, Microforestry is a game that's about microforests. It's a concept of building small, urban, diverse sort of habitats that are surprisingly resilient and very good at capturing carbon. So this game is designed to kind of teach you how you might build a microforest in your own city or neighborhood or backyard. It's a very simple mechanic, basically planting small plants and trying to put them in pairings that work well together. So students always begin with some demographic data. They ask their players for some basic information, both in terms of their age, their education, as well as gaming experience, what kind of games they actually play. This is always really important context, right, when you're studying usability. They ask post-game survey questions in this particular assignment. And in this case, it was really important for the games designers to figure out, does this game teach you how to do something in the real world, right? So games for change or serious games are particularly challenging because not only do you have to like model the real world in a set of rules, but you have to teach the player how they might apply the rules in the game to how the world works itself. In this case, the difficulty was really in understanding how to play the game, and there were a lot of friction there. So, you know, certainly these aggregate results show some sort of serious problems, particularly around whether or not the instructions were clear. But this isn't going to help a game designer, right? It'll just make them feel bad. So students also are asked to do a think aloud, so they try to get more fine-grained, granular detail about where exactly are these friction points, which then lead to potential action items, right? So, for instance, some of the terminology was unclear to players. They didn't understand what WASD is, right? And also, most importantly, in modeling the sort of rules and goals of the system, they didn't understand, like, is the diversity count the number of species? What does this mean? Is this a good thing, a bad thing? So the takeaway here in this first assignment already is that players are building a cognitive model of the game rules and goals, right? So they're trying to kind of extrapolate and understand what those are. They're not always clear. And you can get a detailed understanding of these player models by using surveys, which, you know, as I said before, are great for aggregating response, but not that great for a game design team morale. And then think alouds, which are much better at pinpointing problems themselves.
Okay, moving on. Those are pretty explicit models. We ask the player directly to tell us what they think is going on, but the mind is, you know, largely unconscious processing, forming more implicit models of what's going on, and we can focus on different submodels here. So I want to tell you about a student project that focused on how players perceive their sense of motor control over their avatar in a game. This is Lawrence Dewan, who's an excellent student who we're still collaborating with after the course. And he noticed that delay is a big problem in games, especially in online cloud-based games like Age of Mythology. This is a major pain point for players. They're complaining about lag constantly. And in the course, we talk about some theoretical foundations about what causes players or people in general to feel like they're controlling something. So reading this psychology research, Lawrence came up with a pretty novel idea for how to study and potentially alter players' perception of lag in video games using Dino Run as a little case study. So the general idea was that you could have a visual lag taking place in a game, perhaps due to issues just transmitting data. And this could be really frustrating for a player. But might it be possible to somehow improve the situation by providing auditory feedback, which could be provided locally, so it wouldn't be subject to the same sorts of timing constraints? And could we, with our knowledge of psychology, basically erase the perception of these delays? This was one of the ideas. So there were two conditions here. In Dino Run, the player presses a key, the dinosaur jumps through a long protracted arc and tries to capture coins. We reduced it to 1 coin here. You'll see a demo in a second. And there were 2 conditions. So in one condition, at some point during the game, the player is jumping, and we introduce a little variable delay, where now when they hit the key, there's a little bit of delay before the dinosaur leaps. And in one condition, we provided a delayed auditory feedback cue. So audio cue is delayed along with the visual delay. And here's what that looks like. So you're going to see a few non-delayed jumps where you'll hear me pressing the space bar. You hear the instant feedback and you see the instant jumping. But when the time left counter reaches 90 seconds, we're going to secretly introduce a little bit of visual and auditory lag.
Microseconds.
Yeah, just around like 200 milliseconds with a little variance. Do you hear the delay now, right? You can both hear and see this delay relative to you should hear the pressing of the key, and you can also hear the offset. Okay, so that's one condition. Both visual event is delayed and the auditory feedback is delayed. In our other condition, we instead provided feedback, auditory feedback right when the key press is made. So there's still a visual delay, but the player gets a little bit of feedback right away as soon as they press. And here's what that looks like. So wait for 90 seconds. Okay, you can see they're too late now because it's delayed. But the auditory feedback is more immediate. Okay, so we had a couple of actually conflicting hypotheses about what might happen here. When providing an immediate auditory feedback along with that visual delay, one possibility is that we would get temporal assimilation. So there's plenty of illusions in visual perception research where your perception of visual timing, be it duration or rate or when something happened in temporal order, can be influenced by your auditory perception. So one possibility is that providing this auditory cue would attract the perception of when the jump happened backward in time, thus reducing the perceived lag. But another possibility is that the auditory cue would provide a kind of temporal landmark, making more precise the moment at which the player had hit the key, thus making it easier for them to measure, and all of this is unconscious, I want to highlight, easier for them to measure the difference between when they pressed and when that visual event happened. And in that case, players might become more sensitive to delays due to the feedback. So it could have gone different ways. I want to describe what to expect in this graph before showing you the results. So recall that players do 10 jumps where there are no delays whatsoever. And during that time, we should expect them to hover around the optimal jump lead time. So they need to jump about, I think, 800 milliseconds prior to reaching the coin in order to perfectly hit it. But then at the 10th coin, we're going to introduce this new variable lag. And at that point, we should expect players to slowly habituate to this, to slowly adapt, and start to jump a little earlier and a little earlier until they are again doing well. So we should expect, well, I'll just show you what that looks like. Here's the delayed auditory feedback condition, where at the moment when the jump delay is introduced, the auditory cue is also delayed. And as you can see, the players are learning, but it's a pretty shallow slope. So they're learning somewhat slowly. But when we provide immediate auditory feedback at the moment that the visual delay is introduced, we find that the learning is much earlier. So players are adapting in just 2 or 3 jumps. So it appears that the immediate auditory feedback is helping players to measure that lag and to start to compensate more quickly. We're still theorizing why exactly this is happening. It's a somewhat new result, although it's pre-registered and replicated and somewhat, we've studied it, I think, to beyond the level of certainty that a sort of working game company might need to try and really be sure this is a real effect. So we know it's a real effect, but it's still open why it's happening. Somewhat speculatively, here's a possibility that we think is interesting. When I press a key and I see an event on a screen and there's a delay, One possibility is that I'm just modeling the delay between my key press and what happened on the screen, and then I compensate for that. So adaptation happens between those two events. But another possibility is that players have a somewhat more sophisticated cognitive model of what they're doing when they interact with the game system. So it's possible that I represent myself as interacting first with the computer, and then there's a further leg of the journey where that signal has to reach the game, and a further leg of the journey where that signal needs to reach the avatar. In other words, when there's a delay, the player might need to attribute that delay to different legs of a journey of a signal passing through these different sub-steps of a complex system. So one possibility is that by providing immediate auditory feedback, you tell the player that the delay is not happening between the moment when they pressed the key and when the game received the input. It got the input right away. You're signaling to them that the delay is happening between the moment the game got the input and when the event happened. And this may speed up adaptation, because if the player attributes the delay to the game itself, now it's something they need to deal with. It's part of the challenge that they signed up for when they agreed to play the game. But if the delay is happening outside the game, so to speak, like due to internet connectivity issues, maybe players have a harder time pinpointing that, or they think it's more transient and are less likely to adapt. And I think all of this is, what's most interesting about all this, is just how rapid and unconscious this whole process is. But we can still describe it in terms of the sort of mental model that the player has of their motor control over events in the game. So players' perception of motor control is based on both visual motor and auditory motor regularities, and they can even influence one another. And immediate auditory feedback seems to speed players' adaptation to visual lags.
And as a game designer, I'm like, okay, but so? You know, one area I think we could take this research is asking whether or not this actually improves the player experience. If an immediate audio tone that helps the player pinpoint the degree of lag there might be in an internet-connected or cloud-based game, do they enjoy the game more, right? This would conform to some of Jesper Juul's work in failure and failure attribution, that we feel better about failing in a game if it's our fault rather than some mitigating factor of the game's design or outside influences. So I'm really interested in taking this research a little bit further to understand enjoyability and usability as well.
One other just thought about that is, it's a little unclear whether we should be making our players more aware of lag or less aware of lag. If you make them more aware of the lag, they might be able to adapt to it and improve their performance, but they're more aware of this glitch that's happening in your game, and their subjective enjoyment might go down. So it could be a bit of a trade-off here. Maybe it's sometimes better to keep our players ignorant. But we're actually now going to be digging into this, playing with different degrees of lag, completely different games, to see if we can actually get different effects where we can both enhance players' perception of lag and also suppress the perception depending on the use case.
Follow us on LinkedIn to find out more. Obviously, if we're working together, Ben works in visual perception, so the cognitive model of visual objects and events is very important. It's something that we focus on as UX designers as well. And Ben's going to talk about the science around direct eye gaze and attention.
Yeah, within visual cognition, we can talk about many things, but one of the foci of my lab is social perception. If you think about the visual world, the most important stimulus that we see each day are other faces, and within the face, the most important part of the face is the eyes, especially when they're looking right at you, because that signals that they are likely to act in your direction. Something relevant is going to happen. So we tend to prioritize direct gaze over averted gaze, and this is even though eyes are very subtle stimulus, and you can have just a few pixels difference in an image, but a very different sense of where someone's looking. And in fact, there are all sorts of well-known laboratory findings where direct gaze seems to capture our attention, both in ways that help us, like when we're searching for that direct gaze, but also in ways that can disrupt us, like when we're looking for changes elsewhere in a display. If there's a face staring right at us, it can be harder to notice those other changes because we find ourselves attending to the face.
So what are we going to do to figure this out? We're going to focus on a very classic video game. So one of the things that we ask students to do is work and remake classic arcade games, because we have a limited amount of time in a 15-week class, and we give them about 5 different experiments to do. So they have about 2-3 weeks for each of these assignments. And they built Pac-Man to try to understand this. And this is a slight modification. There's eyes in the spawn box where the ghosts come from that are either directed at Blinky, one of the 4 fantastic ghosts in Pac-Man. So here you see the eyes are focused on the red Blinky character. Otherwise, the game is the same. And then we sort of contrasted that with a condition where the eyes were actually directed at the player. Not the player, I would say, but the player avatar, right? And this is an important distinction, potentially. So here the eyes in the middle of the screen follow your avatar, Pac-Man. We teach students how to instrument their games and collect data straight out of the game. So we measured how many dots were collected in each condition. So in the condition where the eyes are directed at Blinky, this is weird, this is confounding, because in a way, you would think the performance would be worse if the eyes were directed at you, the player. But again, the distinction, player avatar, might be important here. So in this case, the performance is significantly better when the eyes are actually directed at the player. Strange, what's going on? Another thing that's really important is to drill down into this data, and we teach students how to do sort of time-based heat mapping to understand where players might linger, where they go at different timestamps through their gameplay sessions. And individual differences are definitely important here, right? So player 1 has a tendency to kind of stick towards the bottom of the screen, always kind of moves down in the early game. Player 2 always goes to the left, right? So it's important also to understand whether or not this is changing some of the aggregate results in Pac-Man. But the reason we use well-known well-designed games is that they're well-balanced, right? We don't want to have to contend with game design problems in addition to experimental challenges and building a sort of good experiment. Interestingly enough, when examining this heat mapping data, we noticed that one of the players kept sort of dying right by the ghost cage, right? They kind of actually were just kind of going straight there when the ghosts were spawning in the beginning of the game. What's going on here? Well, in this case, the model of visual objects and events, so what we were trying to study was kind of the model of purpose of what the player was doing, and the reason they're playing the game kind of interacted with that. So we recruit our participants on Prolific, which is an online recruiting system, and players are then paid not to do well in the game, although maybe we could change that, but instead to complete the experiment. So what are the incentives there? Well, the incentive might be to finish each round more quickly, aka die faster, right? So here again, it's really important to be looking at the specific heat mapping information to understand much better what's going on. But these are online participants, so we can only really see the heat maps as a trace of their gameplay. We're not over-the-shoulder testing with them.
Yeah, and the other big takeaway there, just to reiterate, is that players have they represent why am I playing this game in the first place? And if you're paying your participants, as has come up a few times already, then they have a very different notion of why they're doing this compared to what we are mostly interested in. And although we think it's useful to divide up these different mental models and focus on one at a time, they also can interact, and we want to finish up with one project that we think illustrates this quite nicely. To start, I want to show you a basic demonstration from visual perception research. This is an inattentional blindness demo, also known as change blindness. So something in this photo will be changing as I flip back and forth between two versions of it. Can anyone detect the change? Don't shout it out quite yet. Has anyone not detected the change? I guess would be my question. All right, give it a little more time. Keep scanning.
Change, maybe raise your hand.
Mm-hmm.
Okay. As soon as you detect it, raise your hand. Keep your hand up if you. Okay, we've got about 30% of the room.
Very nice. Don't worry, there's no correlation with IQ or anything else. Mm-hmm. Oh, it seems to have stopped. Okay.
Oh.
So in case you missed it, the engine of that plane was appearing and disappearing. So now take another look. Yeah, pretty shocking. Kind of important. So this illustrates that when there's a big salient visual change, and when you're not able to compare pixels one moment to the next, that you might not notice a very visible change because you're not attending to it. You need to have low-level motion transients, if you want a fancy term of art, to capture your attention, and then you'll notice a change. Okay, that's one way in which inattentional blindness can occur. If there's a big salient event happening, like everything turning gray, it'll be hard to focus attention on a smaller change that's happening. But inattentional blindness can also occur due to top-down attention, due to our having a goal to direct our attention to some particular target stimulus, as has been illustrated very famously in this gorilla demo. In fact, this work was done by a colleague at our university, so I'll shout out Arian Mack. But the famous gorilla demo comes from Dan Simons. So in this demonstration, I'll ruin it for those who haven't seen it, but I imagine many have. The participant, the demo audience, is asked to count the number of times the white team passes the basketball, and partway through, a gorilla does the moonwalk across the court, and about 80% of people fail to notice the gorilla. And this is pretty surprising to everybody because it's right there. It even crosses through the middle of your visual field, and still you don't notice it. So this is clearly due to inattention. If you don't give the participant the task of counting the number of times the white team passed the ball, they'll notice the gorilla. And it also has to do with the specific visual information that you're trying to select. Note that you're not attending to the black team. You're attending to the white team, and you're suppressing information from the black team. I think that's a big part of why we experience inattentional blindness to the gorilla, is because it resembles the visual information which we need to suppress in order to attend to other information. But the big picture here is that your goals, what you're told to attend to, can influence what visual information you take in. Which led to a straightforward question for games. I think this is you.
When are players going to notice visual changes? Is it more likely that they'll notice it when that change makes it more difficult for them to achieve their goals? So in this case, we used a classic game here, Pong. I'm going to show you, this was a I don't know what you call it, Ben, like a four condition or a four condition design. It's good that we work together and that we present together, because I would never be able to represent all this by myself. In one case, this is a problem. If your paddle gets shorter when you're playing Pong, it's going to be harder for you to win a round of Pong, right? Particularly if it's shorter in relation to the opponent's paddle. So in this case, you see that flash, that interstitial flash. This will make it more difficult to actually visually see, what did you call it?
The motion transient.
Motion transient, or the paddle changing in size. You should be able to see here at this point that on the left, which is you, the player, against a computer player, your paddle's getting smaller. Makes it harder. In another condition, another one that impedes your goals, the opponent's paddle gets bigger. So in this case, the opponent should have an easier time hitting the ball back to you. We don't need to really linger with these. I think you can imagine what happens. It's, I think, a relatively large change. By the end of each round, it should be noticeable, right? what if, this is why we have 4 conditions, the player paddle gets longer. In other words, the change helps your performance. It helps you play well. It helps you win. So if my paddle gets longer, I should be better at this, right? These students did not really design Pong correctly. That's okay. They're psychology students and design students working together. And the computers, the AI has some work. We need to work on that one. But here you see that change. And then what if the opponent paddle gets shorter? Again, the inverse of the earlier experiments where your goals are impeded. So this should help your goal, right? So as I said, this is 4 between subjects conditions. Between subjects, Ben, what is?
Each participant just plays one game. They just see one of those 4 displays.
Okay, there we go. And there was a post-game survey. These games were posted on Itch, and we, again, recruited prolific online participants and asked this question. I won't go through all the questions, but these 2 are interesting. Did you notice anything unusual about the game? What did you notice that was unusual? You know, it's important to ask the general question and get a written response rather than leading them. And then the last question was, did you feel this game was unfair? We want to correlate those things, right? We want to figure out if that's the case. So the results, again, the player shorter, computer longer, in red means that your goals were impeded as a player, and then the blue, player longer, computer shorter, means that it's easier for you to win. It's more individuals noticed the change when their goals were impeded, when it was harder for them to win the game.
And note that the total pixel change is identical, so this is purely due to their attention.
Yep. So we can collapse that data, right? And we can see there's a significant difference between whether or not you see the change, you notice the change, if it's impeding your goal versus whether it's helping you. I guess that's how privilege works, maybe. And those that selected unfair, again, here we have a significant difference. If the change impedes the player, they felt the game was unfair. They both noticed the change in the paddle size, and they also would mark it as unfair. So, you know, easy game takeaway here, it's already been done in games like Mario Kart, is to balance games by making it easier for those who are doing less well than harder for those that are winning. You don't want to make it more difficult to achieve a goal. It will feel unfair in many cases. And this is where we see that actually the visual information that you kind of get in pre-cognitively is applying to your own understanding of the game's rules and whether or not the game is fairly balanced. So these are, you know, some of the models we look at. Obviously, when you're designing a much larger, complex game, many of you work in these contexts, you're looking at all of these together. But we try to help students kind of divvy up these tasks and look specifically at questions around usability, design, visual perception. Some of this might be relevant to visual perception research. Some of it might be relevant to user experience research. And I think, for me, the big takeaway for game design students is that a lot of what we perceive, right, isn't thought about first. It's pre-thought. It happens before we think, and even that influences how we think about a game and how we experience things.
And to give some brief takeaways, we think some advantages of this course are that they put psychology students and design students in interaction during their studies, rather than waiting until they're out in the world and have to meet each other much later. They get to learn by doing, by running actual experiments. It's not really a theory course. We give little lectures, but most of the time is spent building things. And it turns out the process is quite similar across these 2 fields, so everyone jumps in pretty naturally. in general, it's useful to have encounters with this other species before you go off and join a game company. So we see a lot of learning taking place. And we think that the two disciplines can definitely inform each other. We've already seen it in the course. And we'd be very curious from this audience, in fact, the whole reason we're here arguably is to hear from you about what you think we could do to improve this course, or what you think our students should be learning beyond these sorts of approaches and themes. So thank you very much.
Thank you.